Hello, my name is Yu Wang. Today I'm going to introduce the paper GypSum, Learning Hybrid Representations for Code Summarization. There are two main methods in code summarization research direction. The first is AST-based method, which learn representations by transforming code into different structures. The second is token-based method, which directly transfers the technicals from text generation. Here, we use a running example to illustrate the motivation of our paper. As shown in the figure, apart from GypSum, we use two representative models that apply the above two methods to generate commands on the same code. We observe that the summary generated by transformer is detailed and fluent, but fails to describe the core effect of the function. And the summary generated by GypSum describes the functionality closer to the ground truth, but it is too brief and grammatically incorrect. This motivated us to propose GypSum, which leverages two encoders to learn hybrid latent representations from source code. This figure is the overall architecture of our model, which is divided into three parts. First, we use two encoders, the C encoder on the left and the G encoder on the right. The second part is the decoder. We use the hybrid attention mechanism, which makes the model learn from text and graph at the same time. Finally, we propose a dual copy mechanism to copy words from the two inputs. For semantic graph construction, the figure in top left is a sample code, and the figure in the top right is the corresponding AST. First, we tokenize the leaf loads and replace the position with costume load, split load, when the number of subwords is greater than 1, and take the subwords as its child loads. Secondly, we add 5 types of edges, as shown in the figure in bottom right, which is corresponding to the yellow line of the sample code. The first 4 edges has been mentioned in previous studies. Here, we add another edge of control flow. In Figure 3, we show the AST subtrees of 4 common control statements: if-else, switch, while, and for. Take example of the if-else subtree in the top left corner. Binary OP, statement expression, and if statement correspond to the if condition, the statements in the main branch, and the else branch. Since there can be flows from binary OP to statement expression when the if condition is true, and from binary OP to if statement when the if condition is false, we add a control edge from binary OP to statement expression and if statement respectively. Also, once the statements in statement expression are executed, the flow should enter the next statement outside the if block. As such, we add a control edge from statement expression to the next of its parent node. The control edge for other types of control statements are constructed using the similar principle. For G encoder, we use graph attention neural network to propagate our graph, rather than GCN or GGNN, since the attention weights of GAT can be visualized, which increases the interpretability of our model. The update of graph loads is divided into 3 steps. First, for adjacent loads I and G, we use the first formula to calculate their attention score, where HI and HG are the hidden state of them in upper layer. EIG is the hidden state of their edge. Finally, we use liquid relu function to activate. In the graph propagation of each layer, we calculate the score between any nodes by the above way, and use softmax to calculate the weights between each node and their adjacent nodes, and finally use the weighted sum as the updated node representation. To reduce the computational cost, we only take the hidden state of terminal nodes as output. In order to better improve the fluency and readability of the generated text, we choose to use the pre-trained model to encode our code. After experimental compression, we choose the code BERT with the best performance in our dataset. For the text sequence, we first use code BERT to encode and add another linear layer to consist the output dimension with G encoder. For the decoder part, we modified the structure of context attention so that it can handle the input from multiple encoders. As we can see in the formula, attention S is a self-attention module, attention C and attention G is a context attention module handling the output of C encoder and G encoder respectively. We combine them after making context attention and change it back to the original dimension through the linear layer. In order to better generate variable names and solve the problem of OOV, we propose a dual copy mechanism, which copies words from text and graph. PVOC is the generation probability of the original decoder, where DT is the hidden state of the word to be predicted. We separately generate three probabilities, PV, PC, and PG, through DT, representing the probability generated from PVOC and the probability of copy from text and graph. Finally, we use selective log likelihood as our loss function. Referring to the previous work, we selected the two most used datasets, Java and Python. For the design of experiment, we combined a series of baseline models. Our model has made a great improvement compared with the above models on this dataset. At the same time, we performed the ablation study by replacing C encoder or G encoder with other modules. To conclude, we propose a hybrid representation learning method that produces better summaries of the code and use a fusion decoder to learn from multiple encoders. In future, we will investigate the effect of more code representations and other methods for hybrid representation learning. That's all. Thank you.